It's really an honor to be here, and it's wonderful to see so many familiar faces in the audience. So my talk is Approaches to Bounding the Exponent of Matrix Multiplication. This is a problem that I've been obsessed with for too many years. And so this is going to be sort of part survey and then part description of some of the recent work that we've done. And it's based on joint work with a number of people, some of whom are here. You can see them listed there. Let me just start by saying what the problem is. You all, I think, know. We're interested in the complexity of multiplying n by n matrices to n by n matrices where we have, let's say, complex entries. And the standard method, of course, takes n cubed operations. Strassen in 1969 showed that you can do better than that. And that raises the question of how much better you can do. So the exponent of matrix multiplication, omega, is the smallest real number such that you can do n by n matrix multiplication and essentially n to the omega operations up to lower order terms. Okay, and so in those terms, the standard algorithm proves a bound on omega, an upper bound on omega of omega is less than or equal to 3. Strassen proves that omega is less than 2.81. And then there's a whole sequence of works following that over many years that have slowly improved the exponent. Some of these improvements are small improvements, but they represent big conceptual advances. And I'll try to describe many of the ideas that go into all of these works. And then you can see there's a flurry of work in the last few years by Stothers, Williams, and then very recently with in January, I guess, by Legal, that improve over Coppersmith and Winograd's result by just little smaller and smaller amounts. I'll try to say something about the ideas that go into those works as well. Okay, so my plan for the hour is to describe the main ideas behind all of the work from Strassen up until the recent work at somewhat of a high level, but I hope to give you an idea of the tricks that are used, because it seems, I think, from the outside, it seems sometimes mysterious. How do you get these exponent bounds, and what are the improvements that have been happening? I'm going to emphasize 4 conjectures that imply omega is equal to 2, because I think I think that they're accessible conjectures and things that can be proved, and I hope that some of you might be interested in working on. I can interest some of you in working on them. And then I'll describe this approach that I've developed with Henry Cohn and others that involve embedding into a semi-simple algebra. I'll say what that means and describe this, try to portray this as sort of a contrast to the existing approaches which involve bounding the rank of very small tensors and then building up from there. So I'll try to draw that contrast through the talk. Okay, so just to start, I want to say what the setting is. So we're interested in bilinear computations, and the complexity of a bilinear computation basically counts the number of products. So for those of you who are familiar with Strassen's algorithm, you can think of this as the general setting in which Strassen's algorithm fits. You take linear combinations of the matrix A, multiply them by certain linear combinations of the matrix B. You do m of those products, and the result matrix entries should be computed from linear combinations of those products. And so some algorithm that has that form is a bilinear algorithm. And it turns out that that's exactly equivalent to bounding, bounding the rank of what's called the matrix multiplication tensor, and it's denoted by this NNN to indicate n by n matrix multiplication. And the rank bound is at most m, is equivalent to saying that there are m products in the algorithm, the bilinear algorithm that you're using. And I just want to make one comment without talking about the proof. So Strassen, quite a number of years ago, proved essentially that you can take bilinear algorithms without loss of generality. So we're talking about an algebraic problem, and you might think about in general, you might think about an algebraic circuit for it. You might think about taking higher powers of certain entries and doing something that doesn't fit into the nice bilinear complexity format. But it turns out that, as far as finding the exponent of matrix multiplication, it's equivalent to think just about bilinear algorithms, and therefore it's equivalent to think about bounding the rank of the matrix multiplication tensor. So you can define omega both as the exponent of whatever algebraic algorithm you use to compute n by n matrix multiplication, or equivalently as the rank of the n by n matrix multiplication tensor. And I'll say what that tensor is and what do I mean by rank in just a second. So this is the perspective that we'll adopt. That's a very clean mathematical formulation of the problem. And by the way, I should say that please interrupt with questions or comments as I go. Okay, so a tensor, for the purposes of this talk, is a 3D array of complex numbers. I'm going to try to make everything concrete and use lots of pictures, so I hope that helps sort of visualize the problem. And a rank 1 tensor is a tensor in which the ijk entry of this, in this cube, in this array of complex numbers, is xi, yj, zk for 3 vectors x, y, and z. And if you'd like, you can think of the vectors as labeling the rows and the columns and the whatever those things are in the other direction. And then the entry is just the product of the associated x, y, and z values. Okay, and a rank R tensor is one that's the sum of R rank 1 tensors. And a perspective that I'll use for the purpose of making the pictures on the slides is that an equivalent way of thinking about this is that a rank R tensor is one in which the slices of that tensor, if you slice the, parallel to the front face, the slices of that tensor are all linear combinations of R rank 1 matrices. So you have R different rank 1 matrices, and from those you can take linear combinations to get all the slices. Okay, so, and that's actually a very concrete way of thinking of things. And so what is this matrix multiplication tensor? Again, it has this notation n to indicate that you're doing n by n matrix multiplication. And it's an n squared by n squared by n squared tensor. And sometimes I'm going to describe tensors by this trilinear form notation. This is nothing more than a formal polynomial in x, y, and z variables. And the coefficient on a given x, y, z product is the associated entry of the tensor. Okay? So here it is, here's the description of the matrix multiplication tensor in that trilinear form notation. All the coefficients are 1s or 0s. And here it is in pictures, which I think is maybe a little bit easier to think about. So, so this is for a 2 by 2 matrix multiplication. Let me see if I can show you the correspondence. So each slice describes one of the bilinear forms that is one of the 4 entries of the result matrix. So for example, the C11 entry here is A11 times B11 plus A12 times B22. And you can see that there are 1s in the position that pick up the A11 and B11 product and the A12, B21 product if I label the rows and the columns in this way. Okay, and then the next entry in the result matrix is described in the second slice. There's a 1 indicating which products of A and B matrix entries are summed to give this entry, and so on. Okay, I hope that makes sense. You can sort of keep that picture in your mind as we go through the talk. So there are the 4 entries of the result matrix, and these 4 slices put together make the matrix multiplication tensor for 2 by 2 matrix multiplication. Okay, and in general, if I have even rectangular matrix multiplication, n by m by p matrix multiplication, the result is an n by p matrix. And in general, each of the np slices, that's the number of entries in the result matrix, will have a pattern, sort of this block diagonal pattern, where you have 1s in similar positions in the blocks, and in the np slices, they sort of march across the different positions of this block, of which there are m of them. Okay, so that's the matrix multiplication tensor. And the question about the exponent of matrix multiplication, of course, is just a question about the rank of this tensor as a function of n. Okay, so of course, bounding the rank of a tensor is a very different question than bounding the rank of a matrix. We don't have Gaussian elimination at our disposal. It's an NP-hard problem. So you have to develop strategies to try to get some handle on this. And let me start from the very beginning and give you an idea of the strategies people have used over the years to get ever more sophisticated bounds on this tensor. Okay, so the very first idea is the simple one that's already present in Strassen, which is basically a recursive matrix multiplication. A way to describe that in tensor language is to say that if you take the tensor product of the n by n matrix multiplication tensor, I times, operationally that just means you take the tensor, which is the n by n matrix multiplication tensor, and you put a copy of it in each entry of itself, multiplied by the value of that entry, okay? And then you reorganize the indices, you'll find that the resulting tensor is an n to the I by n to the I matrix multiplication tensor. So this implies, together with a fact about the rank, when you take tensors, that the rank of n to the I by n to the I matrix multiplication is bounded by the rank of n by n matrix multiplication raised to the I. Okay, so this is a long-winded way of saying that you can get a bound on matrix multiplication exponent by bounding the rank of a small matrix multiplication tensor by hand. And of course, this is what Strassen did famously with the 2 by 2 matrix multiplication. He showed that you can do it in 7 multiplications instead of 8, proving that the bound on the rank of 2 by 2 matrix multiplication is 7 instead of 8, and that gives you a bound of 2.81 on omega. Okay, so that's somehow the simplest strategy you can use. And unfortunately, it sort of breaks, it becomes unwieldy very quickly. So already for 3 by 3 matrix multiplication, we don't know what the rank is. The current best rank, I've now forgotten the exact value, somebody in the audience may know, it's 21 or something like that, and it gives you a worse bound than 2.81. But this is something that really, many people ask at this point whether you can do a computer search, and if you start to think about it, it's already prohibitive unless you have some additional symmetries or ideas to use, and so things sort of stop at that point. Here's Strassen's algorithm, by the way, just to make everything concrete. Here are the 4 slices of the matrix multiplication tensor the way I pictured them before for 2 by 2 matrix multiplication. And here are the 7 rank 1 matrices that Strassen came up with in pictures. And you can see that, you know, these, let's see, so like for example, this slice is the sum of this matrix and this one, right? Yeah, and this one, this slice is the sum of this, and so on. And you can see that all 4 of them can be found as linear combinations of these 7 rank 1 matrices. So there it is, Strassen's algorithm. Okay, but we want to do something more sophisticated. So the next idea that people had was this idea of border rank. So here you are bounding the rank of a sequence of tensors that approach the target tensor entry-wise. Let me illustrate by an example. So here's a very simple 2 by 2 tensor. Again, there's 2 slices. I'm drawing them for the purpose of the slide. And it's not too hard to show that this tensor has rank 3. Okay, lower bound and an upper bound. On the other hand, it has what's called border rank 2, because if I put an epsilon in this corner here and think of that as a quantity that's going to 0, then I can express both of these slices as linear combinations of these 2 rank 1 matrices with epsilons. Yeah, you can see that I guess the first slice is just this slice, and then this minus epsilon inverse times this second slice is equal to this, right? And so this shows that the border rank, so the rank of a sequence of tensors that approaches the target tensor, can actually be smaller than the rank. And this idea turned out to be very powerful. So strategy number 2 is to bound the border rank of the matrix multiplication tensor for small n. And the reason this is useful is because there's this wonderful lemma that says the border rank of n by n matrix multiplication, that's what this notation means. If that's less than r, then you get a bound on omega which is the same bound as you would get if you were bounding the ordinary rank. So for example, you can make progress by showing that the rank of the 2 by 2 by 2 by 3 matrix multiplication is less than 10. That's the border rank. And from that you get omega is less than 2.79, which is a little bit better than Strassen's algorithm. And the idea behind this lemma, by the way, is a very simple one. If you take high tensor powers of this border rank construction, and you think of epsilon as a formal polynomial, as a formal variable, then all of the entries are degree, if you're taking the kth tensor power, are degree t polynomials in epsilon, and you can just interpolate to pick out the coefficient on the epsilon to the 0. Okay, so somehow in the tth tensor power, the tensor has size was exponential in t, and the overhead that you incur from finding the coefficient on an order t degree polynomial is only polynomial in t, and so it doesn't affect the bound on the exponent. It's a lower order term. Okay, so you can bound the border rank of tensors, a sequence of tensors that approaches the target tensor, and this is an idea that's present from this point on in work on matrix multiplication. Okay. So the next idea people had was to bound not the rank of a single matrix multiplication, but the rank of doing several matrix multiplications in parallel. And the way to say that is it's a direct sum of tensors. So a way to visualize this is that we're talking about the rank of a tensor which has a little matrix multiplication tensor up here, and another matrix multiplication sort of diagonally opposite to it in a way that the computations of each do not interfere with each other. So this is, think of this as doing matrix multiplication instances in parallel. You would take the linear combinations of original two matrices and linear combinations of another two matrices and take products, and from that compute the entries of the two product matrices. So you sort of do everything all together. So strategy number 3 is to bound the border rank of direct sum of small matrix multiplication tensors. And there's a wonderful theorem, a very important theorem called the asymptotic sum inequality that says that if you bound the border rank of the direct sum of lots of different matrix multiplications by R, then you get this inequality involving omega. And so, you know, a single ni matrix multiplication bound would give you ni to the omega is less than R, and here you get to write the sum of the ni's to the omega is less than or equal to R, and this can lead to improvements. In particular, here's an example due to Schoenhagen. The border rank of doing, if you sort of can decode these, this is basically an an outer product computation and an inner product computation together is only 13. Notice that doing this outer product of 4 by 3 outer product of vectors takes 12 multiplications already, and so for one extra multiplication you can think of being able to do an entire inner product. And from this you get a bound of 2.55, which is a big improvement. Okay, and this uses this statement in the box, which is called the asymptotic sum inequality due to Schoenhagen. Okay, so now we can bound the border rank of tensors. We can bound the border rank of lots of independent copies of matrix multiplication tensors all together. And so this is the first.
So in this example, it's not, the ni's are not equal, so it doesn't follow immediately from the...
It doesn't follow me, yes. I've written the square version here. Yeah, so that's right. There's a general version, yeah. You can always symmetrize things. So the matrix multiplication tensor is nicely symmetric, so you can always, if you have an NMP matrix multiplication tensor by just renaming variables, you get an MPN and then a P, whatever, NM, and you take the product of all those and you get a square matrix multiplication. So that's sort of a trick that's used all the time. Yeah, good question. Thank you. Okay, so that's strategy 3, I guess. Then strategy 4 is what's called, Strassen called the laser method, which was a good move because it sounds very impressive, and it is. So the idea there is to study a tensor which is no longer a matrix multiplication tensor, but it's a tensor which has the coarse structure of matrix multiplication, and then that's sort of a blocky structure, and then within each block, that block is isomorphic to a matrix multiplication tensor. And from this kind of tensor, he was able to identify many independent matrix multiplications in a high tensor power to which you can then apply the previous theorem. Let me give you the example that actually led to improvements using this. It's a very simple example, and I'll try to just show you the coarse and fine structure in pictures. So here are a collection of slices, which are, I guess, q by 1 by q by 1 slices. Q is a parameter. And the first slice has, 1 in the opposite corners. The next slice has a 1 that sort of marches towards the upper right corner. And then the last slice of these q slices has a 1 here and a 1 here. And I've highlighted part of it in pink to indicate that the coarse structure, sort of the pink blockwise structure, looks like this. And if you get good at sort of deciphering the pictures, this is an inner product, a length 2 inner product tensor. So that's got the coarse structure of matrix multiplication. And then the fine structure is, for the top thing, it's just a scalar times a row vector multiplication instance. And the fine structure of the column portion is a column vector times a scalar. Okay, so actually very simple, almost degenerate instances of matrix multiplication in these settings. And from this, the border rank of this tensor you can show relatively easily is q plus 1. And then you optimize for q, and you set q equal to 5, and this gives you omega is less than 2.48. Okay. So by the way, one thing that I'm hoping to illustrate as I go through the strategies that people have used is that there are really wonderful and fundamental ideas involved, and then in the end, the bounds that you get still rely on taking very small tensors and bounding their rank or their border rank by hand, and then using the machinery to build up from there. And I think that that's sort of a bottleneck in our way of thinking about this problem. Okay, so q equals 5 gives 2.48. And then I'm going to stop drawing the tensors at this point. Strategy 5, I guess, if we're keeping track. This is the Coppersmith Winograd paper that many of you know from 1987 or thereabouts. So they point out that the border rank of this tensor, which is again no longer a matrix multiplication tensor, but something that has useful structure in it, is q plus 2. So the q is a parameter again. I'm not drawing the pictures, but I hope you can see it's a nicely symmetric tensor if you sort of look at the trilinear form associated with it. You don't have to picture it except to I just want to give you an idea of how this is used. So Coppersmith Winograd show how to zero out variables in a very high tensor power of this tensor in such a way so that you leave lots of independent matrix multiplications, and then you apply the asymptotic sum inequality and go from there. This is a sophisticated proof. There's a probabilistic argument that this is the part that uses explicit constructions of dense sets of integers with no three-term arithmetic progression. That was in the title of the paper. And it's a beautiful result that leads, again, by optimizing q, you end up setting q equal to 6, and you get 2.41, which is an improvement, not quite the full Coppersmith Winograd improvement, but the main idea, I would say. And then strategy 6 is to take that tensor and add a few extra terms. There's 3 extra terms here in red. Again, I don't expect you to sort of visualize this tensor, but I just want to give an idea of what happened in Coppersmith Winograd and what followed. So this has still got border rank q plus 2, so these 3 extra terms come for free, essentially. And you can and they sort of allow you to squeeze a little bit extra out of this. So in sort of very high level terms, there are sort of 6 pieces represented by the 6 terms that you see here. And you have to choose for yourself the target proportions of these in a high tensor power. And how you choose that affects both the number and the size of the many independent matrix multiplication tensors that you can find. And from that, you get the different bounds on omega. So you optimize all those things. In their case, by hand, you get a bound that's 2.388. That's a little better than the 2.41 that we saw previously. And then you can push this idea further by doing the following thing. You can bound by hand the border rank of tensor powers of this tensor. Okay? So instead of starting with that tensor, you start with the square of that tensor or the 4th power of that tensor and so on. So in Coppersmith Winograd, they took the 2nd tensor power and analyzed it. There are 36 pieces. You have to choose the proportions of each of them, and that somehow affects the overall bound that you get. That was what gave the 2.375 that stood for over 20 years by Coppersmith Winograd. And then this recent work has looked at higher tensor powers that are then analyzed by computer. I'm brushing a lot of the details of what they had to do the computer optimization under the rug. Stothers analyzed the 4th tensor power, got a small improvement. Williams the 8th tensor power and got a small improvement. And then Legal was able to analyze the 16th and 32nd power. And then you can see that the number of pieces becomes very large very fast. Obviously, they're not doing optimization over this number of variables. There's symmetries and so on that are exploited. But these are the bounds that they get. And I think, at least the data so far suggests that there's sort of diminishing returns in this particular approach.
Any reason to use, say, powers of 2?
Yeah, they use powers of 2 because the way they manage it is to sort of optimize the previous one and then square it and use sort of the way they've chosen proportions for that in the next one, which is a reason to believe that perhaps, so they're using some shortcuts in the optimization. This is not the best that you can get in any provable sense from that power. Okay, so that's sort of a brief history of matrix multiplication up till, I guess, January of this year. I don't know of any lower bound except that we know that the actual border rank of this tensor is q plus 2. You can't make it q plus 1, for example, which would immediately do that. But so other than those, again, very concrete things, lower bounds regarding specific small tensors, which are the starting points, We don't have a general technique that says you can't go farther than you have with any particular one of these techniques. Sorry to say, yeah.
There's a little-known work from the late 1970s by Gideon Laterman on 3x3 matrices.
Okay.
Now, it doesn't help you in the asymptotic case, but it could be interesting to see how that fits into this framework, because if you use Strawson on a 3x3, you lose. He has better. And if you combine Strawson for 2x2 with his 3x3, you get a better 6x6.
Okay. Yeah, I didn't know about that. Okay.
When Nova asked about always looking for powers of 2, sometimes perhaps mixing it might be.
Yeah, no, and in fact, some of the instances where you start with small matrix multiplication tensors do have things that are not power of 2. It just happens to be that for this particular sequence, powers of 2 were what they analyzed. Yeah, okay, thank you for that. Okay, so what I'd like to do now is to say, to describe several conjectures that would apply omega is equal to 2. This is sort of the opposite approach to difficult problems. You can sort of go right at the boundary and try to push it a little bit, or you can try to think of ideas that would lead.
One question.
Yes.
So, determining the rank of a tensor is an empty-hard question.
Yep.
What's the best known algorithm for give you an A by C, B by C tensor?
To actually compute the rank of it. I don't know off the top of my head. I don't know. I mean, I think it becomes a quadratic program, and I don't know. Maybe probably people in this audience have better ideas than I do. I don't know of anything sophisticated other than sort of generic optimization. Other questions before I do this? Okay. So I want to give several conjectures that imply omega is equal to 2, and I actually hope some of you will be interested in thinking about some of these. I think they're quite accessible. And let me connect it to the previous discussion by talking about first this asymptotic rank conjecture, I guess really more of a question that was asked by Coppersmith Winograd. So you remember there was this tensor that was the sort of centerpiece of their work, the one before I added the 3 red terms. And here's the specialization of that tensor to the case of q equal to 2. You remember there was a parameter q, which is sort of the smallest interesting case. This is a 3 by 3 by 3 tensor, and its slices look like this. It's a very concrete thing. You can sort of memorize this slide and think about it. And the border rank of this tensor is 4. It's known to be exactly 4. But there's a question about the asymptotic rank. So if you take the limit of high tensor powers of this tensor and then take the nth root of that rank, that's a quantity which is at most 4, because the border rank is 4. But it could be smaller, and in fact it could be 3. So if the asymptotic rank of this tensor is 3 instead of 4, then the exponent is 2, which is a pleasing sort of situation.
Also asymptotic border rank?
Yeah, those things are the same, because actually the way you get the bound on the rank from the bound on the border rank is to take a high tensor power, so they coincide. So yes, asymptotic border rank if you prefer. So the question is whether this asymptotic rank is 3. And this, I just mentioned this because, you know, again, this is a question where you just sort of have to sit and think about a tensor, but this is one that has a lot of structure. If you think about what happens when you take tensor powers of this, you know, you get these diagonal stripes of 1s with some holes in them, which is what makes things difficult, but maybe there's a way to approach this and you can actually think about the asymptotic rank and try to prove that it's less than 4, or better yet, that it's 3. No.
So it could be 3.5.
Could be 3.5, yeah.
Then it will give something slightly higher than that?
That's right, yeah, yeah. And it's not, I don't have the equation in my mind, but it's, yeah, it could be a little bit higher. So the question is,
how much bigger than 3 will still be better than the best known algorithm?
that I can tell you, but not online. I can't do it in my head. Yeah. But I think, okay, but I think that any asymptotic bound on the asymptotic rank which is less than 4, although it won't give an improvement on the exponent at all, will be a big deal, actually. Yeah. Okay, so that's one conjecture, which is again in the sort of realm of thinking about concrete bounds on the rank of tensors. One way that you can achieve asymptotic rank of 3 is via this conjecture, which is attributed to Coppersmith Winograd again. It has a very long name, no 3 disjoint equivoluminous subsets. And so here's the question. So if you have a collection of elements from, n elements coming from an abelian group H, they satisfy the no three disjoint equal voluminous subsets property if for every three disjoint subsets of n, if you take the associated sums of those elements, those are not all equal. Not all equal. And so one thing that before I guess I put the conjecture before I wanted to, but I wanted to just point out that if you take the, for example, the group to be z2 to the n, and you take the n different elements to be the n elementary vectors, then that's an easy way to satisfy this, right? Because every sum just has is just the characteristic vector of the set, and so three different sets are going to be three different sums. Okay, so that would be a construction in the group which has size 2 to the n, and the conjecture is that you can take the group to have size 2 to the little o of n and still achieve this. And if you can do that, there's sort of a hashing trick, if you will, that gives you an asymptotic rank of 3 in the previous case. So that's one, again, a concrete conjecture that would lead to omega is equal to 3, equal to 2. And then here's another one. So again, thinking about this tensor about which the asymptotic rank question was asked, we can think of a very similar tensor which has some additional ones, which has a nicer structure. These are the three diagonals. And so the rank of this is 3. It's isomorphic to the cyclic convolution of order 3. And while Coppersmith and Winograd gave a way of zeroing out variables in a high tensor power to get lots of independent matrix multiplications in this tensor, there's a conjecture from our 2005 paper called a strong uniquely solvable puzzle, which I'll describe in just a second, which gives a way to zero out variables in this tensor, leaving many independent matrix multiplication tensors. And it would, if you could achieve, if this strongly uniquely solvable puzzle conjecture were true, you could get exponent 2. Let me tell you what that conjecture is now. This is a disconnected, it's just a combinatorial question, but it's related to this question. I mean, it gives you a way of zeroing out variables. That's the connection to the tensors on the previous slide. So let me just describe this, because I think it's an appealing thing to think about. So we're interested in an array of zeros, ones, and twos of width w and with n rows. And we call it a uniquely solvable puzzle if every time you take a 0 piece from one row, a 1 piece from another row, and a 2 piece from another row, and try to stick them together, namely try to assemble a row from them, you can't do that. So there should be some overlap among the zeros, ones, and twos from 3 distinct rows. Okay, so that means, so in particular, an overlap of at least of 2 or 3 in some cell, because there's 3 pieces being put together, so if there's some overlap, it's either 2 or 3 things. So if you have a uniquely solvable puzzle, you have an array which satisfies this property that any unintended way of assembling the pieces creates an overlap. And our conjecture has to do with something we call the strong uniquely solvable puzzle, which is that every unintended way of assembling the pieces has an overlap of exactly 2 in some cell. It doesn't have to be in all cells, just some cell. And the conjecture is that strong, uniquely solvable puzzles exist with a number of rows, which is w choose w over 3, up to a little of one term in the exponent. And if you think about it for just a minute, you'll realize that a row cannot have, you can't have 2 rows with the same 0 piece, or the same 1 piece, or the same 2 piece. And since in most rows you have roughly equal numbers of 0s, 1s, and 2s, this means that the number of rows, an upper bound of the number of rows you can have is w choose w over 3. And the intriguing thing is that Coppersmith and Winograd showed how to construct uniquely solvable puzzles with essentially w choose w over 3 rows. That was the technical core of their work. And the conjecture is that you can do this for strong uniquely solvable puzzles as well. Okay, and if you do that, you get exponent 2. All the red boxed conjectures imply exponent 2. And then the last conjecture, which is related to the laser method, but I won't make the connection, I just want to state it, is this, what I call the two families conjecture. Here we're interested in n different subsets, A1 through AN, and another n subsets B1 through Bn of an abelian group H, which have the property that AI plus BI are all distinct sums. So if you look at all the sums coming from an AI and a BI, you get distinct values. So there's size of AI times BI, many of them. And if you compare a matched sum, something coming from an AI plus a BI, versus a mismatched sum, something coming from an AJ plus a BK, those should never be equal. And there's a picture associated with this, which makes it a little easier to think about, I think. So if I, again, label the columns with the entries of A1, then the entries of A2, then the entries of A3, etc., and I label the rows with the entries of B1, B2, up to Bn, these conditions state that, and if I put in the entry, each matrix entry, the sum of the row and the column label, these entries in the first condition indicates that in the blocks, these are all distinct values. And that if you compare an entry that's on the diagonal versus an entry that's off the diagonal, those are never equal. And the conjecture is that you can do this for n sets, which are where n is about the square root of the size of the group, and for AI and BI also being about the square root of the size of the group. Okay, and these again are sort of running right up against very simple sort of pigeonhole-like arguments that say that you can't get past beyond that. And again, if you can do this, you get exponent 2. And I just want to say, like a sort of, just to make it slightly more concrete, something you can think about, for example, is to have H be a vector space and AI and BI be orthogonal subspaces of half the dimension. And that gives you the first condition. And that also gives you this, these are about the right size. And of course, then the tricky thing is to try to ensure the second condition, for which you need to do something more. But there's a lot of things, I think, if you stare at this for a while, as I have, there's a lot of things you can imagine trying to do. And again, this is something that gives exponent 2.
Chris?
Yeah.
Is it really important that the group is abelian for the application?
No, all these things can be generalized to non-abelian groups, but then the character degrees start to matter in a way that's harder to express simply. So the conjecture is that you can actually do it in abelian groups. In fact, we know how to do this in non-abelian groups, actually achieving this, achieving these parameters. So there's no group-theoretic obstruction to it, but it's not something that gives a bound on omega. So abelian groups would. And then there's middle ground. If you find a construction in a group with small character degrees, then you're good also, but we don't know how to do that. Yeah?
Is there any natural conjecture that would imply that the exponent is larger than 2?
No, I think because our technology for proving lower bounds sort of can just prove like n squared times log n, and getting something that would be an n to the larger than 2 would be a huge breakthrough in terms of how we can about proving lower bounds on arithmetic circuit complexity. So I don't know of anything except for sort of very concretely when you narrow the conjecture enough to be able to say, well, there's no group that has this property, for example. Something like that. Okay, so I just want to say, so I've presented 4 conjectures. I want to tell you couple words about their status, and then I want to describe, in the remaining time, describe quite a different approach that we've developed with embedding into semi-simple algebras.
So from your answer to his question,
yeah.
None of these are equivalent to the fact that
That's right. None of these are equivalent. So the conjecture about the rank is equivalent, and then everything else are more specific conjectures. But in some ways, you kind of have to have more specific conjectures, because otherwise you kind of have this structureless problem, or structured problem, but one where we can't really get our hands on it. It's sort of okay, that's my perspective anyway. Okay, so these 4 conjectures, the asymptotic rank conjecture, no 3 equivalent subsets conjecture of Coppersmith Winograd, and then 2 conjectures, strongly uniquely solvable puzzles in 2 families we just talked about. And with work a couple years ago with Noga, Alon, and Mir Shpilko, we found some connections between 2 of these and sunflower conjectures that suggest perhaps they're false, but I want to just describe what those connections are so that you have a clear sense of how everything fits together. So there's 2 sunflower conjectures that are false if these 2 conjectures are true. So the no 3 equal voluminous subsets conjecture turns out contradicts the classical sunflower conjecture of Erdos-Redo, which is that every collection of some constant raised to the s many s subsets contains a 3 sunflower. And of course, the famous sunflower lemma tells you that if you have this many subsets, you get a sunflower, s factorial. The conjecture is that constant to the s suffices, and that's a well-known and long-standing conjecture. If that conjecture is true, which is widely believed, then the no 3 equal voluminous subsets conjecture is false. So I would say that conjecture perhaps is unlikely. It depends how much you're willing to believe the conventional wisdom about the sunflower conjecture. And the strong uniquely solvable puzzle conjecture is related to another famous combinatorial conjecture. So here's a conjecture. Every collection of 3 to the n vectors in Z3 to the n contains 3 of them that sum to 0. Sorry, 3 to the n times 1 minus some constant. That's the important part. Okay, so you can't have almost all vectors in Z3 to the n with the property that no 3 sum to 0. That's a well-loved combinatorial conjecture. But I don't think there's a consensus on it. So some people think that you can pack in this many. Some people think that you can prove that you can't. So maybe a 50% chance of being false. And the conjecture that's relevant to the matrix multiplication is a version that we cooked up in the paper, which is a 3-colored version of it. Every 3-colored collection of vectors in Z3 to the n contains a u, v, and w that sum to 0, coming from one from each color class. And because the forbidden configuration is more restrictive, it's perhaps more likely that you can construct a large set. So I would say, just for the purpose of illustrating, maybe this is a little bit more likely to be false. And so this second conjecture, or the strongly uniquely solvable conjecture, strongly uniquely solvable puzzle conjecture is maybe unlikely. And I guess I would just point out that if you're interested in working on that, a warm-up to that would be to try to construct a large collection, multicolored collection of vectors that have no 3 that sum to 0 in this multicolored sunflower conjecture. The other two, the asymptotic rank question and the two families question, as far as we know, are unrelated to sunflower conjectures, and so they're still perfectly good to work on. No hints that they might be false. Okay, so in the remaining time, I want to describe a different approach. This is the group-theoretic approach that we've built together with Henry Cohn and Balash Segedie and Bobby Kleinberg and others. And so this is in contrast to the existing approaches, which, as I tried to point out and I hope illustrated in the examples, have sophisticated machinery but start by bounding by hand the rank of a very small matrix, very small tensor with some structure. And then you build up from there. And so the approach that we, as I said, bound border rank of small tensors, and then you get an asymptotic bound from high tensor powers. And the disadvantages of this is that there's a limited universe of starting tensors that seem to be useful, and high tensor powers are hard to analyze. Okay, so I hope you saw that from the description of the work so far. Okay, so so this idea that we have is to think about n by n matrix multiplication tensor for large n, and to embed an n by n matrix multiplication tensor into a semi-simple algebra multiplication. And I'll tell you what that is. I don't assume that you know all of these phrases. So a semi-simple algebra is an algebra in which multiplication is isomorphic to block diagonal matrix multiplication for our purposes. That is to say, multiplication in the algebra can be expressed as multiplication of matrices with this block structure. And the hope in doing this is that you can do the following kind of reduction. You can embed matrix multiplication tensor into some semi-simple algebra which has this block diagonal matrix multiplication structure. Okay, but at the same time, that algebra should have some kind of nice basis with some combinatorial structure, so that the question of whether matrix multiplication can be embedded into it can be expressed as some question about groups, or as we'll see, coherent configurations or other combinatorial objects that is accessible and you can start to work on instead of just saying you want to bound the rank. Okay, and so you use this nice basis to sort of actually work with. And then at the same time, you know that if you've carried out this embedding, you've reduced n by n matrix multiplication to smaller matrix multiplications. We hope these are smaller. And then you recurse. So this is the strategy. And by the way, when I say embed, if you'd like to think of that as just a reduction, that's also fine. One quick comment that before we leave this slide is that if the algebra is commutative, then this is just diagonal matrix multiplication. All the blocks are of size are 1 by 1 blocks. So the number of multiplications is just then the rank of the algebra. Okay, let me give an example, one where we actually made a good amount of progress. So this is the group algebra. So if you have a finite group, you can think of the group algebra, which is denoted C of G. It's formal linear combinations of group elements. These are alpha sub G's are complex numbers. And you can add those pointwise, and you can multiply them in the expected way. If you multiply group elements according to the group multiplication law, and you multiply complex numbers as complex numbers. And if you write it out, you find that the product of two group algebra elements is some convolution whose structure depends on the structure of the group. Okay, and so in this case, the group elements are what I'm calling the nice basis, in the sense that it gives you a nice way of expressing what it means to embed matrix multiplication into group algebra multiplication. Here's the condition that we worked with in the paper. We're interested in three subgroups of a group that satisfy the triple product property. The triple product property states that if you take an element from the first subgroup times an element of the second subgroup times an element of the third subgroup and get the identity, that happens only in the trivial way, only in the way in which all three elements are themselves one. And if you can do that, you can embed the size of x by the size of y by the size of y by the size of z matrix multiplication in a very natural way. Sorry, I just wanted to leave that for 1 second. So, okay, so in other words, so the question about whether you can embed matrix multiplication is not just the question of can you reduce this to this other thing, but actually a question about finding subgroups of groups with a certain property. So that's the way in which the nice basis manifests itself in this setting. And the theorem that you get from that is related to the fact that the group algebra is a semi-simple algebra. It's the sizes of the blocks are what are called the character degrees of the group. And so you get a theorem that says that in a group that realizes n by n matrix multiplication with the associated character degrees, we get a bound on the rank of, well, however many multiplications it takes to do block diagonal matrix multiplication with those blocks. And that's got a name. It's the sum of the di to the omegas. Okay, and then just to make clear what sorts of things you're trying to optimize here, you can approximate this often quite well by pulling out the maximum character degree times omega minus 2, and then the sum of the squares of the character degrees is the size of g. So you get this, and I'm going quickly because I just want to make one brief point on this slide, which is that the goal is both to embed this into a small group, a group of size about n squared, with subgroups of size about n, and you simultaneously have to worry about the character degrees being small. So you have to think about the representation theory of the group. Okay? And if you can do that, you get a bound on omega. And in fact, we were able to find Reith product groups that had balanced both properties. We get bounds of 2.48 and 2.41 via different constructions. The disadvantages of this approach with groups is that non-trivial results require non-abelian groups. That's something that you can prove very easily. And in our experience, somehow trying to find something that supports matrix multiplication is somehow in tension with the character degrees, and so there are very rare examples where you have something with small character degrees and for which matrix multiplication can be embedded. I mean, maybe that's just because we're not being clever enough, but that's what we found. So this is sort of a difficult thing to balance. Okay. Now, the generalization has a certain advantage, which I'll get to, which is that you can think about something called coherent configurations or association schemes, which generalize groups, and you can think only about commutative ones, so that actually makes things simpler. To do that, I need to talk about how you would embed this in general, and this is, I hope the pictures will tell most of the story here. So again, if you have in general, if you have an algebra specified by a nice basis, which is E1 through ER, and the algebra is given by these structure constants, they tell you when you multiply two basis elements which particular linear combination of the other basis elements you get. It turns out that the tensor of that algebra multiplication is just this three-dimensional array in which the ijkth entry is this lambda ijk. Okay, so somehow this carries all the information about of a general algebra. And when we talk about realizing or embedding matrix multiplication, we're just asking to find a copy of the matrix multiplication tensor in here somewhere. Okay, I won't write down in sort of mathematical terms what that means, but it's literally that. And this leads to an interesting question, one of the things that I hope you take away from the talk, which is the question about weighted matrix multiplication tensor. So when you embed a matrix multiplication tensor in that manner, you get out these, in the places where you're supposed to have ones for the matrix multiplication tensor, you get these lambda ijk's, which are not 0. but they might also not be 1. In the case of groups, these are always 0 or 1, and so we didn't have to worry about this. But what we get from doing this embedding in the most natural way is something which is what we call a weighted matrix multiplication instance. So again, here's the matrix multiplication tensor the way it's supposed to exist. Here's a weighted matrix multiplication tensor where these lambda ijk's are some numbers. Now, I don't know if you can tell from staring at this, but there's n cubed different numbers here, and there's only order n squared entries in the two matrices that you're multiplying in the result matrix. So you can't get rid of this scaling by just scaling the entries of the input matrices and the output matrices.
Okay, so I'm sorry to bother you, triviality, but Z is Ki, we suppose, right?
Yes, this is supposed to be Ki. Oh yes, this is a capital I in PowerPoint. Thought it would be helpful. Yeah. Sorry. Okay, so you have these scaling factors. So in a group algebra, they're always 0 or 1. In general algebras, we have to worry about this. And it leads to this question about what we call the S rank, which is, I think, of a useful relaxation of rank similar to border rank, although it hasn't yielded the same dividends so far. But I hope people are interested in thinking about it. So the S rank, the support rank of a tensor, is the minimum rank of a tensor which has identical support to the tensor that we're interested in. Okay? And so a question that we actually struggled with for some time is whether an upper bound on the S rank of matrix multiplication implies a bound on the ordinary rank. It really seemed just as hard to us, and we felt like if we could get a bound on the S rank by analogy, this should lead to something, but only by analogy for a long time. Here's an example just to make it concrete. Here's 2 by 2 matrix multiplication tensor as we saw before. Here's the result matrix, and I wrote out exactly what's supposed to occur in each entry. And the question, to make it very concrete, about the weighted matrix multiplication tensor is what happens, so we know how to do this with 7 multiplications by Strassen. What happens if you could do a little bit better, but what you got was not what you're supposed to get here, but this term was multiplied by 2? The question is, can you get from there to actually computing ordinary matrix multiplication? And you see the 2, you can't get rid of the 2 by just, you can't divide A1 2 by 2 because that'll mess up that entry, right? You can't divide B2 1 by 2 because that'll mess up that entry, and so on, right? So there's no way to just make the 2 disappear in an easy way. So this is an example of S rank. In fact, we know of examples for matrices where we have a very high rank matrix. Here's an example, which can be, whose S rank is very small because it's, you can get the same non-zero pattern by taking the difference of 2 rank 1 matrices. This is a root of unity. And so the question is, the tantalizing thought is perhaps it's easy to show that the S rank of n by n matrix multiplication is order n squared, or n to the 2.1 or something, whereas it's been rather difficult to do the same for rank. And so we can define the exponent of S rank to be omega sub s. And the nice theorem that we were able to prove is that actually bounding S rank actually does give you a bound on the ordinary rank. So here's the inequality. Omega is less than 3 omega sub s minus 2 over 2. And to see what this gives you, you should think of omega sub s optimistically as being something that's close to 2 plus epsilon. And the bound that you get on the ordinary rank of matrix multiplication is 2 plus 3 halves epsilon. So you get a 50% penalty. But of course, if epsilon is going to 0, then, so if you can prove the exponent, the S rank exponent is 2, then you get that the rank exponent is 2. Is that a 5? Yeah, okay, good. All right. So, okay, and the proof idea I'll skip, but this is indication that this S rank is something you can think about. And then this allows you to think about general semi-simple algebras. And I just want to say a few words about coherent configurations, then I'll stop. So this is an example of a semi-simple algebra that generalizes groups, that uses the fact that we can get bounds on the rank of matrix multiplication from the S rank. And I want to just make one point about it, and then hope to talk more to some of you, or you can read the papers if you're interested. So what is a coherent configuration? It's got points X and a partition of pairs of points into R classes. And it satisfies some axioms, which are the first 2 of which are not so interesting. The diagonal is supposed to be the union of some classes. For every class, there's the dual class where the order of the pairs are reversed. And then the interesting one, which is that if you look at the number of z's, which are distance I can think of these classes as being almost like distances, distance I from x, maybe this picture is better, and distance j from y, then that's an integer which depends only on which class xy or xy was in, and not on the particular value of x and y. Okay, and so, and if there's one class, this is called an association scheme. If these things are symmetric in a certain way, this is commutative. The only thing I want to point out about this is that I have some examples which I'll skip, but it captures a lot of things, including groups, as well as other combinatorial and algebraic structures. There's distance regular graphs are captured by this, Hamming schemes, other error correcting code related things. There's always a scheme based on groups. There's schemes based on group actions, and in this way it generalizes groups. And lots of theory about this. And since I have very little time, I just want to make the main point about this, which is that in this, just like with groups, you have this algebraic structure, and you have an algebra associated with it. The algebra basis elements are just matrices which have ones in the position xy if xy is in the class I, and so you have a basis with R elements. And the three axioms indicate that this generates a semi-simple algebra. Okay, I'm going to skip the details of that. So this is something in which we can think about the embedding matrix multiplication. And just like in the group algebra, the nice basis condition yielded something called the triple product property, which allowed you to think about embedding matrix multiplication by finding subgroups with certain property. You can find something like that in coherent configurations. The nice basis yields something called like triangle condition, which is a little bit like the triple product property, but not quite as pleasing, where you're interested in naming classes according to the entries of the first matrix, the second matrix, and the third matrix, and then a pair from one class, another class, and a third class should actually fit together in a triangle if and only if I is equal to I prime, j equals j prime, and k is equal to k prime. This is again something that you can sort of start to think about if you start to look at examples of coherent configurations. You can start to think about whether the structure exists in there. Sturian configurations come from group actions, and there's a nice condition there, which again, for lack of time, I'll skip, but there's again a condition that you can really get your hands on, I would say. And the point that I want to make is this answer to this question: is this a generalization just for generalization's sake? And I would say no, for the following reason. So in the group framework, we needed a non-commutative group, and that forced us to think about the representation theory of the group, and that was unpleasant. Okay. In the case of coherent configurations, we can prove that under any of the conjectures that I mentioned along the way, commutative coherent configurations suffice, which means you don't have to think about the representation theory of these objects. Any of those conjectures imply that a commutative Sturian coherent configuration, one that's based on a group action, it turns out, would suffice and to imply omega is equal to 2. And so, and I will say, I was going to say how that happens, but let's not worry about that. So the main point, okay, this is the slide I wanted to get to, is that you can think about embedding n by n matrix multiplication into a coherent, commutative, coherent configuration, it's a mouthful, of rank about n squared, and get omega is equal to 2 via that approach. So this is somehow pleasing in the sense that you're just trying to reduce, you're just trying to embed a large object, as large an object as you can, into as small an object of another type as you can, and you don't have to think about anything else. And if you can do that, you get omega is equal to 2, and all of the conjectures that we mentioned along the way imply that you should be able to do that to get omega is equal to 2. I mean, we don't know, but this is a viable approach. Okay, and with that, let me just end with the open problems. So one question about coherent configurations. This is sort of a new approach, and we only have constructions that are based on older constructions. So finding something with a non-trivial bound on omega, so that on the S rank that's not based on an old construction would be a neat example to have in our hands, even if it doesn't, even if it proves omega is less than 2.99. Applications of S rank, this seems like a useful relaxation. For example, we don't know if the border S rank of 2 by 2 matrix multiplication is perhaps 6 instead of 7. Proving that or proving that it can't be would be great. Prove or disprove any of the 4 conjectures. I mean, it would be great if we could prove them, but they're also falsifiable. I mean, they're concrete things that we can prove you can't do. And so any progress in either direction would be really exciting. And then the one that I left with on the previous slide, embed n by n matrix multiplication into a commutative coherent configuration, whatever that means, of rank n squared. That's an approach to getting omega is equal to 2. And I think it's a nice combinatorial algebraic thing. You don't have to know representation theory, and perhaps that's a way to get to solve this problem once and for all. And with that, I'll end. Thank you.
about a crazy idea. One of the problems is that matrix multiplication, everything is discrete, the sizes. So earlier, for example, we described that the optimum was 6 for something, because it's better than 5 and better than 7. But maybe if you interpolate, the best thing would be 5.7, but there is no such notion of a matrix of size 5.7.
Right.
So first of all, you might find a reasonable way where the last element exists or doesn't exist with some probability. I don't know. But another approach how to deal with this is to go to integration instead of summation. So go to two functions, f and g, each of two variables, and define an integral which corresponds to the regular product. Everything is continuous rather than discrete. So is there a similar theory about describing the integral as sum of other integrals?
So there's not a similar theory that I know of. It is something that we thought about and we actually can say something about. So and there's an analogy with the group setting in which you look at Lie groups. And we actually can get, in a certain sense, exponent 2 with Lie groups, except the representation theory is not, we don't know how to integrate it and it's difficult to get your hands on. But that exactly is this question about rephrasing a sort of double integral in a different way, which in some sense gets exponent 2. So that it's in the paper with Lie groups, and I don't know a general theory that goes beyond that particular way of realizing it, but it's a great suggestion, yeah.
Thanks.